Hello. So let us start with the second section of our series of lectures, 4 lectures on eigenvalue, eigenvector, PCA, and LDA. I'm Goutham, and let's start. As I told in the first section, the first section was how to determine eigenvalues and eigenvectors and eigendecomposition of a matrix. The section 2, which we'll discuss now, is about what is covariance matrix, what is correlation, what is scatter matrix, and what are the eigenpairs and principal components. Of course, we already know what are eigenpairs. So in this section, we'll talk about principal components. Okay. So basically, we have a data set, and let us consider that we have a data set of d dimension. But of course, the scatter plot of d dimension is not possible. For visualization, we are using a two-dimensional data. And two-dimensional data means data has two features, say x1 and x2. And we'll explain the correlation of the data of the two features, covariance matrix, etc., all based on the two dimension, but it can be easily extended to d dimension. We will use the letter d for dimension, and we'll use the letter n for the number of data. Okay. For example, for a simple example, let us consider that the first feature is the height of a person, and the second feature x2 is the weight of a person. Okay. So let us, on the left, we have shown the scatter plot of the data. So you can see that there is a relation between height and weight. A taller person, the weight is more. And if you do the scatter plot, we can see that pattern here. Okay. Now, actually, we cannot see in multi-dimension. We cannot do scatter plot in d dimension when d is more than 2. But we can use the same methods, the same mathematical analysis to find the relation between the different features of the data. So let us first consider correlation. Correlation between the two features, x1 and x2, is represented by this equation. Okay. And of course, if the data dimension is d, we can find the correlation between any pair of features. Okay, so it would be ADC2, many. And sometimes you can see that we have a matrix where the entries are the different features. So if you have a d dimension data, then we have a d by d matrix. And the diagonals are correlation between the same feature, which is always 1, but the other entries are correlation between feature 1 and feature 2, feature 1 and feature 3, like that. Okay. So basically, it's okay to see how it works for x1 and x2. The numerator is covariance of x1 and x2. How to calculate the covariance we have shown at the bottom of the slide. And the denominator is square root of variance of x1 and variance of x2. Okay. And if the two features are highly correlated, then the value of the correlation will be nearly 1 or minus 1, depending on whether the correlation is positive or negative. And if there is no correlation, then its value will be 0. If you see the scatter plot, you can see that the slope here is positive. Okay, so if the slope positive means actually if the value of the first feature is over the average, the value of the second feature is also over the average. And if you see on the other side, if the value of the feature x1 is below the average, the value of the x2 feature is also mostly less than the average. Then we have more data on the first quadrant and third quadrant. Then the correlation is positive. Okay. If it is otherwise, if the value of the first feature increases, then the value of the second feature decreases, then the correlation is negative and the scatter plot will look something like this. Okay. The scatter plot in that case will look like this. Okay. And then what is covariance matrix? Covariance matrix, of course, is a matrix, and the diagonal terms are the variance of the different feature. Variance of x1, variance of x2. If you have three features, variance of x3. And the other elements in the row 1 is the covariance between feature 1 and feature 2, feature 1 and feature 3, feature 1 and feature 4, like that. And in the column 1, it will be covariance between feature 1 and feature 2, feature. So it's a symmetric matrix. Okay. And variance, of course, we know the variance of the data is the deviation of the individual data from the average, square it, and then we divide by the number of data. Okay. So for variance of x1, it will be the x1, and variance of x2, it will be the x2 values. Actually, there are two types of variance calculation. This is called the population variance. And in case of population variance, we assume that we have the whole population of data. And then in that case, we divide by n. But it's also possible in many cases that our data is vast and we have only a small sample. In that case, we divide by 1 by n minus 1. And this is called Bessel correction. Okay. So basically, when we divide by 1 by n, then we say it's a population variance. When we divide by 1 by n minus 1, we call it a sample variance because we don't have the whole population of data. We have only a small sample. And in that case, we need that correction. Okay. In case of covariance, similarly, you see, we multiply the deviation of the first feature from its average multiplied by the deviation of the second feature value from the average. Okay, and we average it over all the data. Of course, here also, if we do the Bessel correction, it will be 1 by n minus 1. And here is a numerical example to make it more clear. Say, suppose we have the height data like this, 167 centimeter, 161 centimeter, like that. And we have the weight data, 57.6 kilograms, 64.1 kilogram, like that. Okay. So this is our data matrix. Okay. The first row is the feature of the first feature, which is the height of the different samples. And the second row is the second feature, which is the weight of the different samples. Okay. And of course, if you average height, you have to add all the elements of the first row and divide by the number. That will be the average of height. Similarly, the average of weight. And if we subtract the average from the individual data value, we get this matrix. Okay. So this matrix we call the Z matrix. Because there are two features, it's 2 into n. It's a rectangular matrix like this. And you can easily see that the covariance matrix can be calculated like this. Okay. So again, it is Z into Z transpose, where Z is this matrix. And we divide by the number of sample when we have the whole population available. I mean, the whole data is available. And we divide by 1 by n minus 1 when we have a small sample where the whole population is larger. Then we divide by 1 by n minus 1. And this division by 1 by n minus 1 is called the Bessel correction for variance. So it's actually a repetition. So covariance matrix is like this. And we want to show you with an example that from the covariance matrix, we can visualize the distribution of the data in the feature space. Okay. So in this case, the feature space consists of the height and weight. And from the covariance matrix, you can visualize how the data is distributed in that feature space. Please note that this 0, 0 means covariance is 0. And if covariance is 0, correlation is also 0. Those two features has no correlation. If the value is 1, 1, there is some correlation. If the value is 2, 2, there is stronger correlation like that. And if the value is say minus 2, then the correlation is in the negative direction, not in the positive direction. Okay. So with these three different covariance metrics, and let us suppose the data mean, the mean of the first feature and the mean of the second feature is like 2, 2. So let us see how the distribution we can visualize in the next slide. Please note this is just a numerical example. So, for example, when our covariance matrix is 3, 0, 0, 3, that means these terms are 0, 0 means there is no covariance. No covariance means the data is distributed like a circle. Okay. Uh, by that I mean that the density of the data in the first quadrant, positive, 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 positive. By that I mean the average of a particular data above the average of x1 and the average and the data distribution when the data value is more than the average both in x1 and x2, that we call positive positive. Positive positive data, positive negative data, negative negative data, negative positive data, all are equal in number. Okay, so there is no, you cannot say that if x1 value increases, x2 also increases. There is no such correlation. In that case, the data distribution is like this. Okay. So, and of course, the mean is 2, 2. Let us consider this is 2 and this is 2. So, mean is 2, 2, and the data is distributed uniformly on all sides of the mean. Okay. In the second case, where the covariance matrix is 3, 1, 1, 5, there is a correlation. Okay. There is a correlation and positive, so say it is like this, and the data is distributed like this. Okay. And how to know exactly how the data is distributed? For that, we have to calculate the eigenvector and eigenvalues. Okay. For this covariance matrix, so covariance matrix, of course, we have a general idea that the data in the first feature, its variance is only 3. Data in the second feature, variance is 5. So data in this direction, it is not spread so much. Data in the x2 direction is spread over a larger portion. So these things are, we can guess from the covariance matrix itself. But to precisely understand how the data is distributed, you have to know the eigenvalues and eigenvectors. Okay. So, for example, this is one eigenvector. Okay. So this eigenvector is -1 and this is about +4. So -1 +4, this vector, right? This vector is something like V1. Okay. And in this direction, the data is spread, the amount of spread of the data is the eigenvalue. Okay. So the amount of data spread is 2.5, around 2.5. But if you see the other eigenvector is actually orthogonal to V1. So orthogonal, that's it, it is perpendicular to the first eigenvector. His value is about 0.4 and 0.9, so it is 0.4 here and 0.9 here. And along this line, the data is spread much stronger. You see the variance of the data is 5.4. So data is spread over a broader region in this direction. Okay. So eigenvector shows the direction and eigenvalue shows how much the data is spread on that direction. Okay. So similarly for the third covariance matrix 5, 2, 2, 3, we calculate the eigenvectors and eigenvalues. So the okay, here the first eigenvector is 0.5 minus 8.5. So 0.5 positive minus 8.5. So it's a vector like this. Okay. 0.5 minus 8.5 is a vector like this. And in this direction, the data spread is 1.7. Whereas on the other side, other eigenvector means which is perpendicular to this. Perpendicular to this means this minus 8.5 minus 5.5. So minus 8.5 minus 0.5. In the direction of the second eigenvector, the data spread is much more. The data spread is 6.2. So about 4 times in the direction of, or 3.5 times in the direction of lambda 1. So actually from the eigen covariance matrix, if we calculate the eigenvectors and eigenvalues, we know the direction of the spread of the data and the amount of the spread of the data. So this is very important, and actually principal component analysis is nothing but this. Principal components are these components, this component of the data in the eigenvector direction. And this is the first principal component because the eigenvalue is much more. Actually, I should have put this one as lambda 1, this one as lambda 2. I'm sorry about that. And there is another term which we call scatter matrix. Actually, scatter matrix we'll use when we discuss the linear discriminant analysis. And it has shown that the covariance matrix is the average over all the data. That means if we divide Z transpose by the number of data, then we get the covariance matrix. If we don't divide by the number of data, we get the scatter matrix. So scatter matrix is nothing but n times the covariance matrix. The covariance matrix is 1 by n of the scatter matrix. So this relation, please remember. Okay. So both covariance matrix and scatter matrix are symmetric. So covariance matrix transpose is same as covariance, same with scatter matrix transpose is same as scatter matrix. And they are positive semi-definite, whose definition is if multiply with any vector, the transpose of the vector on the left side and the vector on the right side, the value is always positive. That is, this value is always non-negative. That means it is positive semi-definite. So scatter matrix and covariance matrix both are positive semi-definite. And positive semi-definite also means that all the eigenvalues are either 0 or positive. There is no eigenvalue with negative. And I think in section 1 we have discussed that if the two matrices, the relation is that one is a scalar multiple of the other, then the eigenvectors of the two matrices will be same. So here it's true because the scatter matrix is actually n times the covariance matrix. The eigenvectors are same, but the eigenvalues are n times. The eigenvalues of the covariance matrix we have to multiply by n to get the eigenvalues of the scatter matrix. So again, covariance matrix, actually for the d-dimension data, covariance matrix is a square matrix of dimension d into d. We are discussing with the data of 2 dimensions, so I wrote here C 2 by 2. There's a relation between covariance matrix and scatter matrix. Scatter matrix is G into G transpose. And sometimes we need to calculate in new matrix M, which is G transpose into G. Please remember, please see here, the scatter matrix dimension is D by D. But if we multiply G transpose into G, then the dimension will be n into n, where n is the number of data we have. Okay. Please note that in many practical applications, the dimension of the data is very high, whereas the available number of data is low. Okay, so D is actually much larger compared to N. One simple example is an image. So image, The feature vectors, you can consider the features of an image are the number of pixels. Now, if you have a, say, 25 into 25 pixel image, which is actually not a large image, then we have 25 into 25, 625 dimension data. But let us consider that we have only 50 images or we have 100 images. So the number of images is n. So D is much larger compared to n. Now we have to find the eigenvector of D. Okay. But to find the eigenvector of that big matrix is difficult. So what you can do? We can find the eigenvector of M. And then from there we can calculate the eigenvector of the of covariance matrix or the scatter matrix. Okay. So these are the relations which we use to do that. So this is a scatter matrix. Scatter matrix has D because the dimension is D by D. It has D eigenpairs, D eigen values and eigenvectors, and M dimension is n. So we have n in we have n eigenvalues and eigenvectors. Okay. It is easy to show that the eigenvalues of these and these are same. Okay. But you can ask that, okay, D is much larger than N. Scatter matrix or covariance matrix has a large number of eigenpairs, whereas the same matrix has much less. Actually, what happens, the first N, for example, if we have 100 sample and if the dimension is 625, the first 100 eigenvalues of the scatter matrix or covariance matrix are the same as the matrix M. Okay, so if we and the rest are all zeros. Okay, so out of D eigenvalues, the n eigenvalues are same as that of M, and the rest eigenvalues. So, for example, 625, the first 100 eigenvalues are same as this. And then the 525 eigenvalues are all 0. Okay. And once we have the eigenvalue, we can easily calculate the eigenvector for the scatter matrix or covariance matrix. So this is one way of finding the eigenpairs of the covariance matrix by using a smaller matrix M. So what I have just discussed is written here, and okay, so these three are the important matrices. One is covariance matrix, one is scatter matrix, and one is M. As we already know that the covariance matrix is 1 by n scatter matrix. They have the same eigenvector, and they have eigenvalues which are n times covariance matrix eigenvalues. We know then we can find the scatter matrix eigenvalues by multiplying with n. And this is the relation to find the eigenpair of S. Okay, so if we can find the eigenpair of M, we can use this equation to find the eigenpair of the scatter matrix. Okay. Actually, it will be more clear with a numerical example like here. Say, for example, we again start with the data of height and weight. Okay, so suppose this is the height and weight data. So the average of height is this, the 167, the average of weight is 63. If we subtract this, then we get this matrix, which is our Z matrix. Okay. And okay, it's easy to calculate that covariance matrix will be like this. If we consider the sample covariance, and covariance matrix will be a little different if we consider the population covariance. Okay, so for example, in case of population covariance, we divide by 10 because we have 10 data here. And for sample covariance, we divide by 9 because we have total number of 10 samples. So we divide by 1 by 1, n minus 1, which is we divide by 9. Okay. So here we have the variance of height, variance of weight, and covariance. So correlation we can calculate. So numerator is covariance of height and weight, and denominator is square root of variance of height and variance of weight. If we calculate using this equation, correlation is plus 0.898, which is very high correlation. I mean, for this data, there is a high correlation between the height and weight. From the height, we can nearly find the weight. Okay. So this is a Z matrix, and if we multiply Z with ZT, because it has 2 rows and 10 columns, and if you multiply Z with Z transpose, we get a 2 by 2 matrix like this. And if we calculate the covariance, if we calculate the, this is what, if we calculate the eigenvectors, these two are the eigenvectors. So V matrix is the matrix where the columns are eigenvectors of this matrix. And we have the two eigenvalues. Okay. You can see that this is the scatter matrix, and this is the covariance matrix. Please check that this the scatter matrix is nothing but 10 times of the covariance matrix. Okay, and I haven't shown because these two matrices, this matrix is only 10 times of this. The eigenvectors of this ZZT will be same as the eigenvector of the covariance matrix. Okay, so these eigenvectors here and the eigenvector of the covariance matrix will be the same. And eigenvalues in the case of scatter matrix is 64, 144, and eigenvalues for the covariance matrix will be 6.4 and 14.4 because we have 10 data, and covariance matrix is 1/10 of the scatter matrix. The eigenvalues will be 6.4 and 14.4. Okay. Now, if we find the ZTZ, please see here, the number of dimension is actually less 2, and the number of data is more 10. Okay, so if you do ZTZ, it will be a big matrix 10 by 10. I cannot write the whole matrix here. I just wrote the 4 corner elements. And the more important thing is here is if we find the eigenvalues of ZTZ, then we will see that the first eigenvalue is 64, the second eigenvalue is 144, and all the rest eigenvalues will be 0. Okay, so the first two is same as 64 and 144, same as the scatter matrix. Okay, and this is true vice versa. If this is a smaller matrix, if this is a bigger matrix, even then what will happen? The first eigenvectors here will be same as the first eigenvectors here, and the bigger one will have other eigenvalues as 0. So this is a easier way to calculate the eigenvalues of the bigger matrix. Okay, so that's all for this section 2. In section 3, we'll elaborate principal component analysis and how it can be used to visualize data, how it can be used for dimension reduction. And the last section, section 4, will be about linear discriminant analysis. Thank you very much for listening.